So in this video, I'm going to talk about phase noise. And specifically, I'm going to talk about the linear model of phase noise that was developed by Behzad Razavi in 1996. So we know that a perfect oscillator, let's represent it by this closed loop system here. It's got some forward path gain A. So this might be a ring oscillator where you've got three source followers, or sorry, three common source stages. You've got some forward path gain, and then you feed it back here with unity gain. And if you don't feed it back with unity gain, that's fine. You can manipulate the blocks in such a way that the gain is in fact unity. And you've got this input voltage here, Vn. But what is Vn for an oscillator? You've got this output Vout. Well, we want Vn to be 0 for an oscillator. We want just self-sustained oscillation. So we want this oscillator to produce an output in the absence of an input. But in general, this Vn is going to be our noise. So we want to know if we do have some noise in our oscillator, and this is going to be our entire system, represented by the transfer function h of omega. If this is our system, and it can be anything, again, this is just a very general model, then h of omega describes how the system shapes the noise, so how the system responds to the noise. And if we've got our ideal oscillator, we know we've just got a couple delta functions at plus or minus omega naught, where omega naught is the oscillation frequency. But in reality, so this is our oscillator's output with no noise. In reality, we're going to have some noise as an input. And so these delta functions are going to get smeared into something that has finite height and something that spectrum is more spread out. And we're interested in finding what does this tail, let's call it a tail because that's what it looks like. What does it look like? Do we have a function that can describe how this oscillator looks in the presence of noise? And that's going to be the goal of this video. So we know that ideally our oscillator is operating at a frequency of omega naught, and the only transfer function that matters is h of omega naught. And h of omega naught is just these two delta functions. That might seem a little weird. Transfer function can be delta functions, but that will allow us to get some interesting results from analyzing this. So in general, this noise is going to change the frequency of our oscillation, because if you add another random signal to a perfect sinusoid, it's not going to be a perfect sinusoid anymore. So it's going to be some omega naught plus a delta omega. And the delta omega is used to represent the noise. Now, in general, the frequency change is going to be a function of time. So this model isn't strictly speaking correct. But it will let us get some valuable results that are approximately correct. So that's why we proceed with using it. And it is commonly used today in electrical engineering. So we know we can represent the closed loop transfer function h of omega as a of omega divided by 1 plus a of omega. And this is important because this is going to let us characterize the transfer function only as a function of the open loop gain, which is what we want, because we know the open loop gain. If it's a ring oscillator, for example, say it's got 3 common source stages. So it's got one common source stage, another common source stage, another common source stage, which I'm drawing as inverters because I'm lazy, and they're connected together. Then we know that a of omega is just our a naught cubed divided by 1 plus s over omega RC cubed, where RC is just the time constant. And I go over the analysis of the ring oscillator in a previous video, and we'll go over it as an example for phase noise in the next video, but that's just the basic idea. So if we want h of omega plus omega naught plus delta of omega, so some value about omega naught, then we can get that by saying, well, what's the value of a at some value omega naught plus delta of omega divided by 1 plus a of omega naught plus delta omega. Well, this isn't immediately, it's not immediately clear what we should do from here on out, but a reliable fallback is just to use a Taylor series expansion. So we can evaluate A at some omega naught. We can evaluate it at another omega naught. So let's just say that A of omega naught plus delta omega is equal to its Taylor series expansion, or A at omega naught plus some delta omega times the derivative of A with respect to omega, evaluated at omega naught. And strictly speaking, it's a pure derivative, not a partial derivative, but they're effectively the same here. Okay, and I've neglected the higher order terms here. So in reality, the Taylor series expansion would have an infinite number of terms, but we're only going to use the first two because that's what we're most interested in. We want an approximate result. We want a starting point, something that we can sink our teeth into. So if we just substitute in these two terms into the expression above, we get that that's equal to A of omega naught plus delta omega dA omega naught d omega divided by 1 plus A of omega naught plus delta omega dA omega naught d omega. And you might say, well, you've done absolutely nothing interesting. Why did you bring us? Why did you take us through this pain? But remember that this is an oscillator. So the oscillator's transfer function, which we know is just A of omega divided by 1 plus A of omega. We know that an oscillator at omega naught has A of omega equal to minus 1, or A of omega naught equals minus 1, because that's at the frequency of oscillation. So we know this A of omega naught of our oscillator. So this A of omega naught is negative 1. And so if we plug in negative 1 here, then we cancel with the 1. If we plug in negative 1 here, it's not immediately obvious what we should do, but we can say that, okay, well, this term we're going to say is much smaller than 1. And if that's true, and it generally is, because our omega naught might be extremely large in the gigahertz, and delta omega might be as small as kilohertz or megahertz, and the derivative need not be large, then we're going to say that we can neglect this too. So the only thing that we're left with on the top, only thing that we're left on the top is negative 1 divided by delta omega times the derivative of A with respect to omega at the frequency omega naught. Well, now we're kind of getting somewhere. So this is an interesting intermediate result. And in fact, this is actually the final result. It's just we're going to expand this a little bit. So what does this say? Well, this says that h, our transfer function, looks like 1 over delta omega. And it's multiplied by some constant, which is this derivative at a point. But overall, we expect the frequency response to look like this, where this is omega. And this, say, is a distance from our operating frequency omega naught. We expect our delta function to be smoothed out like 1 over omega. Or I should say 1 over delta of omega. Well, we can make this result more computable, I guess, because we know that, let's say we have A of omega, so we have the forward path gain, and since we're designing the oscillators, we always have the forward path gain. And say we're interested in the derivative dA at omega naught d omega. Well, we know that A can be written as the product of two functions, the magnitude and the phase. So e to the j, let's say phi of omega naught. The derivative of this. And so we can just use the product rule to expand this derivative, u prime v plus v prime u. The derivative of the magnitude, in general, we don't know, but we can just say it's the derivative of the magnitude at omega naught multiplied by the phase. This is just u prime v plus v prime u. So we're just differentiating with respect to omega. Plus v prime, which is j times the derivative of the phase with respect to omega, multiplied by, oh, and then still we've got the exponential term, because that doesn't go away when you take the derivative, multiplied by u, which is our magnitude. And if we're only interested in the magnitude of this whole function, then we can get rid of e to the j. We can get rid of e to the j anything, because this magnitude is just 1. And we're left with the square root of the real part, which is this first term, or the derivative of the magnitude squared, plus the imaginary part. And remember that a at omega naught is just minus 1. So the magnitude of this is 1, and we can cancel it out, just like the magnitude of e to the j phi anything is 1. So plus the imaginary part, d phi of omega, d phi evaluated at omega naught, d omega, squared. And so this is our final result. This is dA d omega. And if we're interested in the overall transfer function h, or approximate h, we know it's just 1 over delta omega times dA d omega, or dA omega naught magnitude derivative squared plus the phase derivative squared. And the math might be a little intimidating, but it's really just the product rule for a complex number. So there's nothing to be scared of. And this is our final result. I'd suggest you go through and try and get this yourself, just so that you can understand where everything comes from. But it's if explained properly, it's a fairly simple result. It's basically just saying that our transfer function, which originally was a delta function, actually gets smoothed to something that goes like 1 over delta omega. So it still blows up at omega naught, as we would expect it to, is omega naught. But in the vicinity of omega naught, so we don't know what it actually equals at omega naught. In the vicinity of the omega naught, it goes down like 1 over delta of omega. 1 over delta omega. And so that's how we find the phase noise of a linear system. And this is a very approximate answer, because we've ignored the fact that our system is in fact time variant. And in the next video, I'm going to go over an example of, well, that's great that we have the magnitude of the phase noise, or the magnitude of the transfer function. We know what our oscillator looks like, but how do we actually compute it if we have a specific architecture? So I'm going to go over the 3-stage ring oscillator in the next video.